let's start with some audience participation now. But that's me. Let's get me off of there. Yesterday, I talked about the future, the new things. Today, I promise there will be nothing new. Okay? If you're in here expecting something new, well, they just closed the doors. I'm sorry. Audience participation. Okay. How many in here feel familiar, or somewhat familiar with C#? Okay, it's quite a few. How many do not? Okay, one there. That's it. That's you. Well, this talk is for you. Sorry, everyone else. So, also, how many feel somewhat familiar with functional programming in any way, shape, or form? Okay, quite a few. That's good. So, by and large, those of you in the intersection of those two groups, you're probably going to get twice insulted today, so that's going to be really fun. I have a lot. The functional journey of C# gets longer and longer, so I might not take a lot of questions during this. I intend to in principle, but when I look at my timing, it's probably going to be off, and I'm going to try to catch up. And so if you have questions you don't get to ask during the talk, come and talk to me after. I'm going to be around for the rest of the conference, so I'm happy to talk to you all the way through. So the way that this is going to work is I'm just going to be in Visual Studio. We're going to start with C#1, and then we're going to use the evolution of C# to talk about various functional concepts and how they have translated into C#. Okay, so hopefully it'll highlight some concepts some of you might not have heard of or not thought of in that way or something. That's kind of how I'm going to approach it. And hopefully everyone learned something or feels enlightened in some way. If not, I'm sorry. As I said, I don't have any rabbits I can pull out of a hat today. So we're just going to start off in C#1 with a little program. I'm immediately like, this is breaking my rule by a little bit of not being able to fit a program on one screen when I do demos. So I'm going to cheat right off the bat. I'm going to switch into what you can think of as C# demo mode, which is I'm going to use top-level statements, even though they didn't come into the language until much later. So let's just go and use the excellent refactoring here. Convert to top-level statements. Good doing. And now we're on one screen, so we're good. So C#1 right out of the gate was, another object-oriented programming language. It had some completely accidental similarities with another popular object-oriented programming language at the time, and sort of trying to embody the view of that time of what object-oriented programming was. There was already like a hint of something functional sneaking into C#1, which was that there are actually first-class function types in C#. So you have these declared function types that we call delegates that represent a function that you can then have a first-class function that you pass to another function, or use as a value. And now when you receive it, you can call it inside of the body here. When you pass one, you have to have a declared method or function, but then you can pass it by name, not invoke it, but actually pass the function along. So this is like this rudimentary first-class functions support already in C#1, which is one of many things where we diverged from some of our random inspiration out there. Okay? But it's not a lot, but it allows me to do some high-order programming here. I'm filtering the array that it comes in using the predicate. So I'm executing it multiple times, using it for real functionality. This is something that would have been more tedious to write in some other language. So good, all right. But we really sort of start getting into it in C#2. So the really annoying thing here in this code here is there's a cast here when I get things out of my array list. Okay. So we should talk about polymorphism. Polymorphism really just means you can write code that applies to multiple different types. Right? You write it once, it applies to multiple different types. And object-oriented and functional programming, they each have sort of their core version of polymorphism, and they're quite different. Object-oriented programming has subtype polymorphism, which means that all your types are arranged in a hierarchy. There's an ISA relationship between them, and at the top sits object, and everything's an object, and everything is everything along the path up to object. So that means if you just write code in terms of object, it'll work for any type, every type, in fact. Right? So we can have things like ArrayList, which can contain every type because it can contain objects. So that's great. You can put many different kinds of things into the same collection. But the downside of it, of course, is that when they come back out, you don't know which one it is, so you're going to have to use context and your knowledge as a programmer to somehow be right about what it was and cast it back out to that strong type. Functional programming, being about functions, they take a much more function-oriented approach to polymorphism. And they say, well, it's not, they say that polymorphism, we can call it parametric polymorphism. It's not about being able to have everything, but it's about being able to have anything, which is different. So they have like generic types that we are now adding to C# and C#2, where they say there's a type parameter, and you can pass in a type argument for it, and now you have a list. You can have a list of anything, but it's not a list of everything. And you have to say what the anything is. And in this case, I'm saying that it's a list of int. And now it's strongly typed to only be able to contain ints. Great. Everything seems to work, and my little cast here is grayed out, so I don't have to die a little inside every time I look at this code anymore. I have strongly typed code now because my intermediate collections here are strongly typed. So that also means that they can have strongly typed helper functionality on them. And so instead of me kind of laboriously generating my own return array here, I can get a strongly typed array just by saying dst.toArray, right? It has a toArray method that returns a strongly typed array. Great, awesome. So I just ditched 2 lines of code. It's a great start. Let me see. So there are benefits to generics that just kind of come out of that. But also, I can use generics myself, of course. Actually, step back a bit. We had list of int here. Generally, we have now strongly typed collection types. They have element types. So we don't actually need to use arrays as our interchange type anymore. It's the only collection type in C#1 that has a strong element type. So you're kind of forced to use arrays, but they suck as an interchange type. They're way too specific. They're way too dangerous because you can easily accidentally mutate somebody else's array and so on. So now we can do something that's more sane. We can abstract more on our boundaries, and we can use other collection types, including collection interfaces. So let's go through and do that first before we try and declare generic things on our own. Okay, that kind of does that. Okay, now we can make our own generic types. So let's make one here. Predicate doesn't have to apply just to ints. It can apply to all things, or anything rather. And now we just have to say which thing it is, and we're hunky-dory. And now we have predicates for everything, or anything. Of course, we can have generic functions as well, so that's great. Let's make this able to filter anything, not just ints. And all we have to do is go and I'm going to do it manually, but I haven't timed whether it's faster to do a search and replace, but I'm going to put a shit ton of T's in here. So if you're a coffee drinker, sorry. There we go, right? No red squiggles, that means it works. That's the functional ethos. If you don't get errors, it works. And I'm going to just apply that without any evidence here. Okay. So now we have a generic filter method. Great. You know the benefits of generics. You notice here that even though the method is generic, somehow I wasn't forced to give it a type argument. And that's because another thing functional programming languages, strongly statically typed functional programming languages tend to, because of parametric polymorphism, types tend to get rather big and complicated sometimes, but it doesn't really matter because you usually don't have to say them. There's a lot of type inference going on. Now, we want to copy some of that. That's really convenient. We can't do as much as you do in a functional language because actually of subtype polymorphism. There are many situations where we can't predict with the same certainty as a pure functional programming language. We can do some. There are other object-oriented languages that do more or more type inference than we do. We kind of want to be a little cautious on that and like not infer things from far away in the code. So the only thing we infer based on, in this case here, we infer type arguments based on parameters, or based on arguments to the function in question, and only that. Not on like what's the return being used for, or what does some other file say somewhere else. So it's kind of cautious, but it still takes care of like an important number of scenarios here. So that's type inference. Okay, that was polymorphism. Another thing that you often see in functional programming languages is a quite sophisticated relationship with lists. and you know, collection-like data structures are typically kind of list-like in functional languages. And one of the things you can do is you can have something I call list comprehensions, which is a pretty advanced ways of producing lists programmatically, even as they're consumed on the other end. So in C# we add what sometimes called generators. In C# we call them iterators, which is the ability to write a function. So it's a method or function that returns IEnumerable, the interface. And instead of producing an output collection explicitly, you can just yield return individual values, and you don't really have to do anything else. Then the compiler will generate for you something that implements IEnumerable, and that whenever you for each it and call move next, it will sort of gradually execute this body until the next value and the next value and the next value is produced. Again, concept started out in functional programming languages. Many other languages have it now. And one last thing is that, okay, this having named functions is kind of heavyweight. Why don't we have some sort of anonymous function expression in C#? So we add what we call anonymous methods, and this is our first attempt at having function expressions in C# functional style. It's kind of clunky, but it's there. We put the delegate keyword, and then anything else from the method stays the same, except there's no name and no return type. Right? So now we can do that. And finally, we're like, okay, it seems to be good to have some of these generic function types. Let's put predicate in the library and just say that it's something everyone can use. So got rid of a lot of code, and it's safe, and it's neat. That's C#2. Okay, so in C#3 though, if you thought that was a lot of functional stuff, you know, C#3 is all about taking, it seems like everything we can scrape off a functional programming language and piling it together in service of querying. Querying is the mission of C#3. We want to slay querying, you know. We want to take everything related to query and we want to unify it and beautify it and make it all crisp and general and beautiful. And for that, we sort of pull out all the stops with functional programming. It helps that we have some functional programming Haskell luminaries like Eric Meyer join the effort at this point to really kind of infect our brains with functional ideas. So let's build up to that gradually. Like you'll notice that filter is already sort of a querying method, right? So we'll build on that and kind of get all the way to full querying capability here with some shortcuts. So first of all, okay, this is kind of clunky, right? You know, it doesn't feel like a small expression that you can just plunk in all the time. It feels kind of heavyweight. So let's have it already now in the next version of C#. Let's have a do-over. Let's have proper Lambda functions. Let's get this syntax kind of cleaned up. We jumped the gun. We did something that wasn't very elegant and that couldn't be, you know, improved based on the current syntactic regime. Let's have another one. So now we have Lambda expressions. Remove the delegate keyword. Put in the arrow. But beyond that, there are all kinds of ways that you can improve on that. First of all, the body here, if it's just like a return statement with a single expression there, let's just allow you to have an expression body directly. Right? You just have an expression body. It's great. And also, the parameter list, you know, it gets converted to some delegate type, and that delegate type here it's predicate of int, right? We use type inference on the array to get the int, and then we have a strongly typed delegate type, predicate of int. We don't need to say int again; it's already there. We could just infer that. So we can. There's a version of lambdas where you don't say the parameter types. Okay. And finally, if you have just one implicitly typed parameter, let's even ditch the parens, right? So now it's like really nifty. This is like full functional niftiness. Okay. You're like, oh, can't believe this. You can write super cool church numerals in C# now. You know. So that's all good. Now we want to use a bunch of query methods like this together. But one thing when you use kind of this functional style that gets annoying pretty quickly is if when you compose functions and apply multiple ones at the same time. And functional programming languages have a solution for that. So since I only have one function up here, let's just apply it twice. So let's say we want to filter the output of a filter Imagine those with different functions, right? Now I have to do it like this, you know. I put some other lambda here. Let's say we want all the even numbers. See if I can write that out real quick without messing it up. So that works, but it's clunky to read. Like the first thing that happens is in the middle, and then the next things that happen kind of glom onto both sides of it. And where do you start reading this expression? So in any respectable functional language, you have an alternative syntax for function invocation. That's a pipelining syntax. Okay. So what that really means is that the first argument, or the argument to the function, comes in from the left. So it can look something like this, and this is not going to be valid C# code for a while, so bear with my squiggles. Something like this. Let's just abuse the shift operator here a little bit. So I'm taking the result of this and I'm piping it into the next function. And now it kind of comes from right. So we can even do it twice, right? We can start out like that. Let me take the filter paren again here and move it. So we can take the array, pipe it into the first filter function call with the remaining argument, and then again to the second. And if we then start, you know, arranging them on separate lines and so on, it starts to flow really beautifully. Okay, the things that belong together, sit together, and you start with something, it kind of flows through transformation, and it comes out the other end. It's called fluent, right? It's fluent man. Anders always said you should never say the word fluent without also saying man, because it's so hip. Yeah. The only thing is, like, we don't really want to add another operator to C# for this. And it's also kind of, it gets into details. But we think of a better way to do this, and that's extension methods. Okay? So I'm going to now turn filter into an extension method. So real quick, we need a static class. Let's call it something innovative like extensions. And then we need the paren to be at the end. Did it go to the end? No, it didn't. There we go. Indent. It should be static because the class is static. It should be public because we want to use it from the outside. So that's a static method now. If we put a little new keyword on here, call it the keyword this, now it's an extension method. And what that means is it's still a static method, but it gets to pretend that it's an instance method on its first argument. Great. So that means that if we go up to array and press dot and start filtering the methods here, you see that filter is now, it shows up there. Okay. So now we can actually, not only can we go and do fluent programming using the dot instead of a new operator, but we also get the discoverability, right? That when you press dot, you get a finite set of things you can apply. You don't have to search the universe for, is there a method or is there a function that might work here? So you pay something, you have to declare it explicitly as an extension method. It doesn't work for all functions. But on the other hand, you get the discoverability, which is really the dot discoverability, which is really cool in functional programming. So this is an example of us adapting a functional concept to fit better into the object-oriented world instead of just grabbing it and slapping it on. And extension methods have really had they've been super useful in many scenarios we didn't even think of. So they have a strong afterlife. And you saw my talk yesterday, we're thinking about revamping the syntax so that this concept becomes even much more generally applicable than just instance method-like things. Okay, extension methods, great. Now we build a whole library of extension methods to do querying. They get fancier names that fit better with SQL, to be honest. They're inspired by SQL, but they also flow better when you look at the fluent style here. Array where something. Like that just reads nicely. And because these are now a library along with join and group by and select and whatnot, select many, then I don't have to declare my own anymore. But now you know how it's declared. That is literally like the code of the first implementation of where. So nice. But we want to solve querying not just for in-memory objects. We want to solve querying for, we want querying to work the same when you're working against, for instance, a SQL database. SQL database, we keep saying for instance, but back then that was really the thing that we cared about, SQL database. And how do you do that? Well, we reach back to an old functional language, Lisp, arguably the first functional programming language, if you accept the lambda calculus itself, which didn't really run. So Lisp had this note. If you look at the Lisp program, it's all parens and words. That's all it is. And it's a strong principle in Lisp that code and data are the same. Right? They look the same, and you can easily quote some code and treat it as data. So there's a very permeable boundary between code and data. In other words, so code quotation becomes a way of taking code and working with the structure of the code as if it was data. You get a data representation of code, and now you can do meta programming. Right? Meta programming comes from Lisp. So code quotation shows up again and again in functional programming languages later with various syntaxes and to various degrees. F# has a whole quotation system, for instance. Can we do quotation in C#? And can we do it so elegantly that you don't even notice? Yes. And the way we do it is with an interface called iQueryable. So let's say that array was a database table. It would implement the interface iQueryable. It isn't, so I'm just gonna explicitly turn it into a queryable. But what then happens is that when we call the where method here, you see that it has a different, the where extension method that applies to iQuerybles has a different signature. It doesn't take a delegate anymore. The function that comes in is not treated as a delegate. It's treated as an expression. That means the compiler sees that and it knows to, instead of build a function for you that you can call, it builds a syntax tree of the thing that people wrote in code, a syntax tree of the Lambda itself. And then the where method stitches that together, consecutive calls, all the other query methods as well, consecutive calls, and builds up a big syntax tree of the whole query you just did. And then when you consume it by iterating it here, it goes and translates that into SQL on the fly, passes the SQL onto the database, gets something back, and presents that back to you as another iQueryable that you can then do a next query on, and so on. So really neat, and you can't even see the difference down here. It's just different overloads of where being called. So that's sort of like the key of where LINQ gets its unification from. And you may like or dislike some parts of it from a performance perspective, but it really kind of nailed it from a functional perspective. No pun intended. Last thing, kind of needs, it would be cool if it really looked like SQL and not just like when you squint. So we actually add SQL to C# pretty much. We have a syntactic sugar for this whole thing where you say from I in that thing, where as a keyword. We changed the order of these, but otherwise it's pure unadulterated SQL. Okay, where's a keyword again? Just remove the lambdas and just put their bodies there as expressions. And at the end, there has to be a select. So let's do that. So I erased too much, sorry. There we go. Still strongly typed, right? And there you go. This is syntactic sugar for the other thing, but it looks like SQL, except that the select comes at the end because that's the only sensible place to put it. Otherwise, how do you know what type I is when you select things? You have to declare it first. Okay. So far so good. We've done LINQ, language integrated query. It's all cool. And then we don't do so much functional stuff for a while. But I should point out that I didn't say why this was functional. But the query expressions in C# are a special case of what functional languages often call monads, and then people run away when functional evangelists start talking about monads. But F#, for instance, has a thing called workflows that supports a certain way of structuring code that's similar to what we just saw. And this is a sort of query-specific syntax for that. But in F# you can solve many things with workflows or monads, including querying, but also including async. So in C#, C#4 we do dynamic, has nothing to do with functional. In C#5 we look at async, and F# has already done it at this time, and they used monads as a generalization that could be applied also to async in a very elegant way. And we ended up not doing it the same way. We looked at it for a while, and we ended up deciding that this did not fit well enough with the imperative style that's still dominant in a language like C#. So we didn't go their way. We chose to do async a different way. Still a little reminiscent of monads, but only if you squint real hard. It's much more imperative oriented. So nothing functional in C#5. now we're going to change example and go to a different example. I would come to C#6. And again, nothing much functional happens in C#6. There's a little bit of lambda envy. Lambdas are so nice, methods are so clunky. Could we also just have expression bodies in named functions and not just in lambdas? Okay, sure, let's do that. So we do some of those in C#6. You can just do that. Happy now, and it gets a little more expression oriented that way, which is cool. And then in C#7, we kind of do the rest of them. We didn't do all the different kinds of members in C#7. We're like, we can do the rest. It's fine. We complete this, and now people can be expression bodied all the way as long as they only have one expression in each body. But we now get into a few other things that start to become important. The cloud. So let's talk about another fundamental difference. It's kind of related to the two different kinds of polymorphism in a way that we talked about in the beginning, but another big difference between functional and object-oriented programming is how, when you have multiple different kinds of things, how do you have behavior that is dependent on which kind of thing you're looking at? How do you have type-dependent behavior? And there are two fundamentally different approaches to that between the two families of languages. In object-oriented programming, we use two virtual methods. So if I have types arranged in a hierarchy, the base class will have some virtual method that it declares, and then all the derived ones will say, okay, this is how I do that. This is how I implement this function. This is my approach to doing what is abstractly the same function, okay? This is just my way of doing it. So it's encapsulated with the types. You can have as many new types as you want derived from that original base class or interface, and you can just add new ones all the time because they bring their own solution to the question, what should it do when this function is called? Okay? Functional programming kind of turns it on its head. So instead of saying mads.render here, they would say render mads. And they would declare just one function. Let's write that function. I'll try to write it. String render takes a person, P, does something. Let's make it expression based since that's so cool apparently. And now inside of the body of a single function, they handle all the different types. Okay? Let's try to do that with what we have at the C#6 level. So okay, that as a base case, we should probably get the whatever the person does. That's the fallback. So let's grab that as the body for now. Put it here, and we see immediately one thing, which is when you do it the functional way, you have to grab the data that you rely on from the outside, right? So you can only depend on public data in the things you're looking at, in the types you're looking at. But that's cool. Separation of data and functionality, that's, we know that one. And now, of course, I have to deal with all the derived types. In this case, I have only one for the sake of the example, but that could be many. And I deal with them in here as well. So I have to sort of say, let's use the question colon operator, the ternary operator. Let's say if it's a student, P is student, then do the student thing, otherwise do, fallback to the fallback. But we would chain more of them if there were more. So let's take the student thing and do it. And it's just as easy, right? We just take that, we put it in there, we put p dot in front because we have to reach in from the outside, and p dot last name, that's great, p dot id, we're done, right? Well, oops, persons don't have an ID. Oh, that's annoying. So now again, we're back in a similar hell that from context we know that P is the student because we asked the question earlier. So now we have to cast it explicitly to student here in order to also tell the compiler, yes, it was a student over there, but it's still a student here, even though everything's mutable and it could have changed. We're verifying that it didn't, hopefully, We hope. Unless there are more threads and they mutate. Let's just bet on this here. So it's both kind of unsafe and clunky in a way, right? Because it's not parallelism safe. And of course, this is not how functional languages do it, because this is what they do this is how they do the thing. They don't have virtual methods. Like, let's actually get rid of them here. They just have this, so it has to be better. And what they use is pattern matching. Pattern matching is the key here. Pattern matching and switching on patterns, essentially. So we ease into pattern matching in C#7. We have student S here, we can say now, and this is now a pattern. And a pattern is a new thing in C# at this point. What is a pattern? It's essentially a test. It takes a value, and then A, it performs some sort of test on that value, and if that test succeeds, B, it can extract some of the data resulting from that test into new fresh variables. So in this case, it checks that it's a student, so it's a type pattern, and it extracts the thing as a student into the fresh variable S, which means now we can just go and say s.I here, and we solve the immediate problem of the cast. Right? So that's nice. And we only have a few kinds of patterns here. Constant patterns are another one, like you can say is null. But the only places you can use patterns in C#7 are in is expressions, like here, and then in switch statements, where they previously could only use constants. Now they sort of get retconned to having the same kinds of tests they can do, but you have to stay within the existing syntactic confines of C#. And of course, that's not super elegant. Switch statements are not super elegant. Let's just agree on that. So in C#8, I think it is, we're like, okay, let's copy the functional programming language some more. Let's have a switch expression instead that does pattern matching in an expression style. So you can say p switch here, and then open curly, and at the end there's a close curly, and semicolon here because this is an expression body. And inside of that switch, what we have is pairs of patterns and expressions for if that pattern succeeds. So the pattern student S here means that we have this string as a result, and otherwise the catch-all pattern, the discard pattern, the default pattern triggers on anything. Right? So it looks a little neater, and you can imagine if we have many things, that we kind of get a neat list of, in order, if this is true, do that, if this is true, do that, this is true, do that. Code gets much more neatly organized and easier to read, but it also gives you stronger checking. So for instance, if I forget to do if I forget to do the catch-all, I'll get a little warning on my switch saying, hey, you're not handling everything. You sure you want to go like this? And even more strongly, if I do them in the opposite order and I handle everything before I get all the way through, then it'll tell you this is unreachable and that's unacceptable to me. Go fix your code. So it helps you kind of it gives you more honesty in checking in your code. So that's pattern matching. We do add some functional languages. Pattern matching is the bread and butter, as I said, in many ways. Certainly for this type-dependent behavior, and they have many more and more advanced patterns, and we've been gradually adding patterns to C#. So for instance, if we want to avoid the index out of range error here, if the first name is empty, we could add a case that is a recursive pattern. It says, well, let me use a property pattern here to check the first name, and if that first name satisfies the pattern constant empty, then do this here instead, then just print the last name. Or we could use a list pattern to say, if this list of characters that a string really is an empty list, then let's do that. So I'm applying patterns at the next level down, or I could even grab it in a pattern that always succeeds, var f here, and then put a when clause on. That is just a Boolean expression saying when string dot is null or empty, for instance, of f. So I can even mix it with a Boolean condition here. Okay. So recursive patterns, tuple patterns, list patterns, they're all recursive, and they kind of use patterns further down the structure of the value. Okay. So that's what I wanted to say about this, I think. And we have just one topic left, and I think I have time for it. I have 4 minutes, right? Okay, got to rush a little. No, I have more because they started late. Let's just see how long they let me go. It's not lunch after, right? So I'm not keeping you from lunch. Okay. Immutability, okay? Object-oriented programming, you have objects, they have identity, their state evolves over time. Functional programming is kind of more mathematical. Values are values. You don't change them. They can't change in sort of a pure functional mindset. Instead, what you do when things evolve, you get new values from the old ones. Okay. So first of all, we're not very good with immutability in C#, so let's fix that. I could. I wrote this wrong, didn't I? Right line. There we are. Was that wrong the whole time? That must have been bothering the heck out of you. Okay. So after I create the student here, I could just go and change it, right? Object-oriented style, mads.last name equals Nielsen, which I actually used to be my last name before I got married. So somebody evil is trying to change it back here. I don't want that. I want mads to be immutable. Well, thank God, a couple of versions ago here, we introduced the ability to have getter-only auto properties, so I can just remove the setter and we're good, right? Well, now the object initializer doesn't work anymore either. It stops me from doing this, but unfortunately also from this nice syntax. So here we add the init version of the setter. An initter is a setter that only works until the initialization is done, until you reach this final curly here. And then it's no longer legal to use it. So it kind of draws the right line between the mutation I want and the mutation I don't want. When the object is initialized, you can no longer mutate it. Great. That's awesome. Okay, how do I mutate an object when I can't mutate it? You have to use a pattern called, what's often used is a pattern called non-destructive mutation. Okay? So what does that look like? For instance, and you can do that without any language support. For instance, person could have a method called with last name, and then when you call that method, you give it a new last name, and it returns a new person object that's the same as the old one, except with the last name changed. That's a lot of boilerplate for everyone to write. Just go and look at the Roslyn compiler, which was written before what I'm about to show you. So a lot of with methods, What if we could support that automatically? In general, what if we could support that value view on things as opposed to the object view? What if we could be sort of immutable value semantics by default? Well, that's what records are for. So here we get record. I'm cheating a little bit, but you can say record class or you could say record struct. You can only actually say all that in C#10, but be that as it may, we have records. And they just flip a lot of the defaults and add a bunch of functionality to the classes and structs that it's added to make them behave more like values. And one of the ways that they can behave like values is that they support non-destructive mutation directly as a new language feature. So when you have a record, you can say old mads, the mads that had the Nielsen as his last name, equals mads, the current mads, with and then an object initializer body here. And boom, right? You get I have to say var. I forgot to talk about var. You kind of get type inference, functional, we love it. So I'm creating a new mads from the old mads with just a single thing changed. It's a copy except for what I put in the object initializer. So that's supported by records. And actually, another thing that's supported is that they actually have a really good two-string implementation. Because they're values, it's easier to do one without worrying about cycles and stuff. So we actually, when you print them out, they look really nice. So let me print out a few things. But I'm also going to print out something else, because one last thing, it's not the last, but one more major thing that we support is value-based equality. So if I took old mads, if I say, is mads, the original mads object from up there, is that equal to old mads with the last name changed back? I mean, clearly they're different objects, but they have the same values inside now, right? So they should be the same. And let's just see if they are. So let's print. You can see the nice two-string there, and then you can see that they are indeed value equal. And you think, well, that's easy. Value equality is easy. It's not actually when you are dealing with object hierarchies, because what it's actually checking here is whether two student values are the same. but it only knows that the student value is a person. Because statically, here, when this equality gets compiled, it doesn't know that it's talking about students. The compiler doesn't know that it's generating code for comparing students. So essentially, equality has to somehow be virtual in the objects themselves so that it can make sure that both the before and the aftermaths are both students and that they have the same values even for the student-specific values that aren't statically known at this point. So equality is implemented virtually, and try to do that correctly yourself, and that's going to kill you. So, I mean, it took a bunch of language designers a while to figure out how to do it in a way that always works. But we did, and it's there. I'm not going to tell you how, because we're out of time. But that was sort of the last thing, immutability, the last thing that we embraced, not to force it down your throats, but as an alternative when that's the style that works out for you, when working with immutable objects saves you from parallelism problems with shared mutable state. If you're not mutable, you don't have shared mutable state. Hooray, parallelism, and so on. So that was kind of the last turn of the crank here before we get into the future, where we'll probably have more functional inspired stuff in C#. I hope that was helpful and interesting to you, even though, again, I didn't bring anything fancy and new, but maybe I brought you some perspective. Maybe I got some folks with pitchforks saying, that's not really functional programming. And I want to end by saying, no, it's not. If you want to like fully experience functional programming, go and write in F#, because that is great, and you will either stay there forever and be my guest, as long as you're still using Azure. But also, you'll come back a better C# programmer. And you'll find that you have a lot of the tools at your disposal that were good for you in the functional space. So that's kind of how I'll end this and say thank you very much.